So I've got this trio motor. It's like the Japanese style metric, 3000, 6000, 23-bit, 17-bit, absolute encoder. Looks like a good motor. We're going to take a closer look at the feedback device on this. Otherwise, it's a pretty standard motor. So it's an MXL. I got the 04 here, actually A, and flange 06, and speed, that's 3000 RPM. Actually, you could hit 6000 max speed with some higher voltages, like 240. This is a 200 volt or 400 volts, so 240 volts AC rectified gets you pretty close to doing the 5 kilowatt. I'm going to use the Xenus Compact, which is a 2.5 kilowatt. So we can get pretty much most of these motors here with one drive. This letter L or T, so 23-bit. There's a battery, so it's multi-turn, and the T would be 17-bit. So I got the 23-bit here, and looks like a brake option and different connector options. So just, yeah, your basic, I'm going to say, low cost, but I know Trio, so good quality. There's some speed torque curves, and they do provide some data. So the 04A is 2.9 amps RMS. That's times the square root of 2 for Copley, so a little bit more continuous. And then there's the peak current, probably 2 or 3 times that. Yeah, so it says 11.5. So I got the 15 amp drive here, so that should be fine. Inertia, peak and continuous torques, rated speed, max speed. The data that they don't show is the resistance, but you can measure it. Mine's 4 ohms. I just guessed 4 millihenries. It's actually twice as much for the inductance. And the feedback, 24-bit. If it had a brake, 24 volt. And the torque constant, so torque divided by the current is a torque constant. From that, you can derive the back EMF constant. And we'll take a closer look at this, but just wanted to show that there was some cables associated with this. So we have the drive side connectors, and so the pinout is from the drive perspective. So I had to, it's not very many wires. There's like a loop back from the battery pack to power. It's 3.6 volt lithium for multi-turn storage. So that goes to the battery, and then you get data back and forth and 0 to 5 volts. So, what is the feedback device on there? It looks like a Nikon A type format. So we're going to hook this up as an absolute A, and the Xenus Compact, 120, 240. Again, 7.5 amps continuous, 15 peak. There's a larger drive and a 2-axis drive, and there's some features in Copley that we might take advantage of that maybe we can't do stuff in the EtherCAT Master. So there's still a reason to use Copley, even though they make a drive. But the motors are looking good. So absolute A is 2.5 megahertz, and I've got the wiring diagram here, and it's showing the shield connected to the case of the motor. Like, I normally cut that, so just shield outer braid to the drive. I didn't see an inner foil, but if there is an inner foil, that could go to the signal ground. Outer braid goes to the frame ground, and it's just bidirectional data with some battery that powers the encoder. You can see on the connector for the feedback where the S and S knot are. One thing I did learn was CME 8.1 needs a feature to ignore an LSB. And I also did a downshift from 23 bits minus 2, so 21 bits. So I get 2,097,152 counts for 1 rev. I just did a 10 rev move, so it tuned up nicely. XL run, decel, move and settle. That's a lot, 2 million counts per rev, so plus or minus a few counts for settling should be fine. It turns out it's a 10-pole motor, so rotating at one time, you see 5 electrical cycles. That's good information for phasing. The cable, I just cut this end off and made sure I got the pins right, because again, it's from the drive perspective. So the green-orange is S and S knot for bidirectional data. The battery pack loops back to the encoder, so I just put a little jumper between the red yellow and the blue yellow black. And then of course the black is ground and gray is plus 5 volts. I did the soldering myself, burned my fingers. I'll get someone else to clean it up for me later. But the basic data we enter normally is 23 bits, so 8 million counts per rev. You can't go 6,000 RPM with that. So you got to knock down a few bits to get some higher speed, but maybe you don't need to go 6,000 RPM. So, and then multi-turn, I'm assuming 16-bit, but that's a lot of turns, and 2.5 megahertz. You could ignore the battery, but I've got one, so I might as well use it. So the problem I had was phasing. It all started off looking nice, 100 degrees of offset going forward, counts went up, that was all good, but the needle turned twice as fast. So I got out of phase within one electrical cycle. But the correction was, given that CME sets the value and it doesn't set a bit, I read the manual. And the manual says, hey, number of LSBs to discard from reading. So we'll have in the future 8.1 and ignore so many bits. And we ignore 1 bit. So that's all I did was set bit 16. And so that's, I click on 16 here. I get this 1. And I write it down, set in flash 0x12A. That's the motor feedback parameter, and I set the bit, and then the phasing worked perfectly. And then, to enter the motor data, I had to downshift, and then that way I can go, well, over 6,000, but 2 bits of downshift. So I did 2 for downshift, and then saved the flash, and that screwed things up, so I had to write to that bit again. But in the future, we'll have a checkbox in here for ignore how many bits of non-existing data there is. Anyways, we'll take a look at the CME setup and configuration. And so the basic setup is selecting an absolute A encoder. And you can see change settings, absolute A, and 2 downshifts, give me 2 million counts. There's no ignore bit here, so I'll do that over the serial port. But I'm not gonna save anything here yet. But if you had a break, you come to a controlled stop and put it in the EtherCAT mode. That's very popular with the Trio, or I guess any EtherCAT master, but use the Trio. So the Trio model. Motor model number 10 pole. There's inertia in the data sheet, peak and continuous torque. I divided the current, like Newton meters per amp, of course, right? Amps RMS is different than amps peak. But once you get that, you can drop that in for the back EMF, same number, volts per kRPM, 34 volts per kRPM, measure the resistance. I said 4 millihenry, but it turns out to be like 8 millihenries. I don't have the meter with me, but the current loop tuning with the calculated values came out to about 1 kilohertz, but my current is 3.87 because the motor is in amps RMS. So you can see that I did some tuning here for the current loop, but I got the limit set there. This calculated out to 3,000. I want to go 3,000, so I put in 6,000 here. That's just a safety limit. And you can see tuned by a human. And then if your inertia load is large, you just knock this down to 100. So 10-to-1 ratio, no problem. It's 1 to 100, and you got to knock this down to 10. I dialed back on the feed forward a little bit, but let's see if we have to look at the tools manual phasing. So 0.3 amps. There's a little lag going here with the red, little lag, so it's very balanced. You could do 2 amps. But the important thing on the phasing is as you go forward, counts go up. So you can momentarily set to 0. I mean, it's absolute. So on power cycle, it'll come up with the absolute multi-turn position. But you can see the counts going up. When I'm rotating forward, counts go down. When I rotate reverse, I had an offset here. And it's like, well, that's 180 out of phase. So I just put in 180. And I wanted clockwise, and then I made the counts go up by inverting the motor and then inverting the feedback, and then press the enter key. It's all phased, so phase is good. Quick peek at the tuning, current loop, of course. If the gains are too high, let's stop auto setup, hit start. If the gains are too high, you get some ringing. You can really see the ringing there. So cut it in half. Still a bit of ring, cut it in half again. If the integrator is too high, you get some integral windup. You can kind of see it there. Yeah, there's the integral windup. So still winding up. So let's knock it down. That's pretty good. That gave me about a kilohertz of current loop bandwidth on the bandwidth test. And I like the calculated value should be about a kilohertz. The auto tuning should be about a kilohertz, and the manual tuning should be about a kilohertz. Oh, perfect tuning. Perfect tuning by a human. And then we can do a little velocity loop tuning, set the parameters, auto setup checkbox. Let's look at the current, make sure we're not exceeding anything. I dialed that down. Let's go a little bit slow and do 3 hertz. Bang, 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 forward and reverse. And you can see it doesn't quite get there. I did get some oscillations. I doubled the gains, buzzed, cut it in half, still buzzed. So cut it in half again, buzzing went away. For the integrator, and you can get some integral now to get to steady state. That's pretty good. We're going to put a position loop around it. So this will be 1 electrical cycle. And so 2, what's the count, rev? So 2097152 is 1 rev times 10 is 10 rev. Trajectory limits, let's go 3000 RPM, 500 for XL DSO. Let's throw a little S curve on there, see what it looks like. I got some error while I'm moving, and then it settles because I adjusted my feed forward gain, 16,384. This is good for point-to-point move and slide into position. If you need more aggressive moves, you could, of course, do trapezoidal commutation. Maybe there's a little integrator wind up. I can knock it down a little bit. Let's give it a little less integral and see if it lands a little better. So this is plus or minus a few counts. You can tweak the integral to get it to settle better, but allowing some error while you're moving might be the solution here. If it's a scanning application, you're running at velocity, it's 16,384, but this has a little less. There's a little cog in the motor. It's not like a slotless design, you know. It's got a little cog to it, but it's not bad. So the error didn't look bad while we're moving. So I think we should be good. There's cog compensation in the Copley. We could use that. That's a benefit or a feature of using a Copley, plus the cross-coupling features that are very popular and pulse at position for lasers, even though the EtherCAT Master might not be able to do it. Copley can. So I guess, yeah, at the end of the day, did your tuning, save the flash, save a file. I'm going to save a motor file here so that if I get the next motor, I already have a file for the motor, the range of motors. And then for this drive, Xenus Compact 23015, you could save a CCX file. And what's it called? Trio, XEC, bang. Good. Well, thanks for watching. Trio is a good company. I'm familiar with their EtherCAT Master. Their motors seem to be fine. I'd rather you didn't use their drives, but hey, you know, it's a little competition. So thanks.